This video lecture, we will discuss the main properties of linear circuits and their behavior in sinusoidal and periodic non-sinusoidal regime. We will now get deeper into the properties of linear circuits, which we have already partially introduced in the video lecture about sinusoidal circuits. We will in particular discuss the properties of time-invariant linear circuits. These are linear circuits whose parameters remain constant with time. From now on, I will refer to these circuits simply as linear circuits, implicitly assuming that they are also time-invariant. One property of linear circuits that we have already mentioned when talking about circuits in sinusoidal signal regime is the following one. Suppose that we apply at the input of a given linear network a sinusoidal signal Vi of t. So a signal in the form Vi of t equal to Ai, the amplitude of the signal, the cosine of omega t plus a phase phi sub I. Then the signal Vo of t at the output of the same linear network will also be sinusoidal and will have the form Vo of t equal to A sub O, the output amplitude, the cosine of omega t plus phi sub O. The output signal, besides being sinusoidal as the input signal, will have the same angular frequency, omega, while the amplitude A0 and the phase phi 0 will be in general different from Ai and phi I in the input signal. So, whenever a linear circuit is stimulated with a sinusoidal signal, the circuit responds or provides at the output a signal with the same sinusoidal shape and the same frequency as the input signal. Instead, the circuit will, in general, change the amplitude and phase according to its features. We also know that if we could have a detailed look at the network inside the black box representing the circuit, we would find out that all the currents in the branches and all the potentials at the nodes of the circuit have a sinusoidal behavior and the same frequency as the input signal. This is a fundamental property of a linear circuit, so much so that this property can be used to define a circuit as linear. So, if a circuit is linear, it has this property about sinusoidal signals. On the other hand, if a circuit has this property about sinusoidal signals, then that circuit is linear. Another important property of linear circuits, not without connection with the previous one, is relevant to the superposition principle, which we also have already met in one of the previous video lectures. In particular, if a circuit is linear, then the superposition principle holds for that circuit. This statement is true also in the other way around. If a circuit complies with the superposition principle, then that circuit is linear. Let's go through the superposition principle once again. Let us consider a linear circuit and suppose we apply a signal Vi1 at the input of the circuit. Be Vo1 the signal at the output of the circuit as a response to Vi1. Here, Vi1 is called the cause, while VO1 is called the effect. Suppose now we apply a different signal, Vi2, at the input of the same linear circuit, and that the circuit responds to this stimulus with a signal VO2. If the circuit is linear, then the superposition principle holds. This means that if we apply at the input of the circuit a signal which is the sum of the two signals Vi1 and Vi2, the circuit will respond with the sum of VO1 and VO2, the signals we got as individual response of the circuit to Vi1 and Vi2. So, to an input signal which is the sum of the two different causes, the circuit responds with a signal which is the sum of the two effects. We know that this result can be extended to as many input signals as we like. This is called the additivity property. Besides this, if we take the same linear circuit and we apply at its input the signal Vi1 multiplied by a real constant A, then the circuit will respond with the corresponding effect, VO1, multiplied by the same constant A. This property is called homogeneity. We know already that the superposition principle, besides applying to linear circuits, is also a powerful tool for circuit analysis, in particular for those circuits featuring two or more independent sources. We would like now to start discussing how a linear circuit affects the amplitude and the phase of a sinusoidal signal. We will do that with a simple example. So let us consider a very simple linear circuit, just consisting of a capacitor, which is a linear component. We know that in the phasor domain, if I is the current provided by the current source, then the voltage across the capacitor, the phasor Vc bar, is equal to 1 over j omega c, the current I, since the current flowing to the capacitor is exactly the current provided by the current source. The phasor I bar can be expressed as an amplitude I sub I times e to j phi sub I, which is the phase of the phasor. If we take the modulus of the phasor, what we get is exactly the amplitude I sub I, and if we take the phase of the phasor I, we get phi sub I. We know that in the time domain, the current provided by the source can be written as I of t equal to I sub I, the cosine of omega t plus phi sub I. The voltage Vc across the capacitor can also be expressed as an amplitude times e to the j phi c. In the time domain, this phasor Vc is translated into a sinusoidal signal Vc of t equal to Vc, same amplitude as that of the phasor, the cosine of omega t plus phi c. According to the above equation, the modulus of the phasor Vc, which is simply Vc, is equal to the modulus of 1 over j omega c times the phasor I, which is equal, as we know, to the product of the modulus of 1 over j omega c times the modulus of the phasor I, which is 1 over omega c times I sub I. The phase of Vc is instead given by the phase of 1 over j omega c times I bar, or the phase of 1 over j omega c plus the phase of the phasor I, which is equal to the phase of minus j over omega c plus the phase of I, which is phi I, while the phase of minus j over omega c is the phase of a purely imaginary number with negative imaginary part, which is minus pi by 2. So overall, the phase of Vc is minus pi by 2 plus phi sub I. And this is, of course, equal to phi c. So from our previous discussion, we got that the phasor Vc is equal to I sub I over omega c times e to j phi I minus pi divided by 2. In the sinusoidal domain, this phasor corresponds to the signal Vc of t equal to I sub I over omega c, the cosine of omega t plus phi sub I minus pi by 2. Incidentally, this last result tells us something we already know, which is that the voltage signal in a capacitor lags behind the current signal by pi by 2. More important, this result tells us something about the way a linear circuit may change the amplitude and the phase of a sinusoidal signal. In particular, the amplitude of the output signal, Vc of t, is inversely proportional to the frequency of the signal. The phase is instead changed by a constant value, minus pi by 2, independent of the frequency. More in general, the change in phase introduced by a linear circuit may depend on frequency. What we have been discussing up to now is just a specific example. Or in general, if we have a linear circuit with at the input a phasor Vi equal to an amplitude V sub I e to the j a phase phi sub I, the phasor at the output, VO bar, will be equal to a coefficient depending on the frequency, alpha as a function of omega here, times the amplitude of the input phasor, times e to the j times the phase phi sub I plus a change in phase delta phi function of the frequency omega. In the sinusoidal domain, the input signal will be of the kind Vi of t equal to Vi, the amplitude of the signal, times the cosine of omega t plus the phase phi I. Again, in the sinusoidal domain, the output signal V of t will be equal to alpha function of omega times V sub I times the cosine of omega t plus phi sub I plus delta phi of omega. The two functions alpha of omega and delta phi of omega represent the way the linear circuit acts on the amplitude and the phase of the input sinusoidal signal. Alpha of omega and delta phi of omega together represent what is called the frequency response of the linear circuit. In particular, as we will see, alpha of omega represents the modulus of the frequency response, while delta phi of omega represents the phase of the frequency response. We saw that the frequency response of a linear circuit with its modulus and phase indicates how the circuit modifies the amplitude and phase of a sinusoidal signal. So, if we know the frequency response of a circuit, given a sinusoidal signal at the input of that circuit, we can work out the amplitude and the phase of the signal at the output, which will be again a sinusoidal signal with the same frequency as the input signal. We may wonder whether we are able to do the same in the case where the input signal is not a sinusoidal signal. For example, consider the case where the input signal Vi of t is given by the sum of two sinusoidal signals at different frequency. So A1, the cosine of omega 1 t plus phi 1 plus A2, the cosine of omega 2 t plus phi 2. Since the circuit we are dealing with is linear by definition, then we can apply superposition principle. So if the frequency response of the circuit, and in particular if the modulus alpha of omega and the phase delta phi of omega are known, then the output signal V of t will be given by A1 times alpha in omega 1, the cosine of omega 1 t plus phi 1 plus delta phi in omega 1 plus A2 times alpha in omega 2 times the cosine of omega 2 t plus phi 2 plus delta phi in omega 2. This result, as we said, has been obtained by applying the superposition principle. In particular, the output signal has been obtained by adding the effect of the first term in Vi of t to the effect of the second term again in Vi of t. Of course, this result may be extended to the case where Vi of t is the sum of how many sinusoidal signals we like, each at a different frequency. We may now wonder how a linear circuit affects a signal which is not sinusoidal nor the sum of a finite number of sinusoidal signals, but is nevertheless periodic. Before considering this case, let me recall the definition of a periodic signal. A periodic signal is characterized by a period t. A periodic signal is a signal complying with the following relationship. The signal at the time t, v of t, is equal to the signal at the time t plus the period for any real t. For example, the square waveform represented in this picture is a periodic signal. The period of this signal will be the time distance between two leading edges of the signal, or equivalently, the distance between two falling edges of the signal. Incidentally, in the case of a square waveform, we can define a characteristic parameter which is called the duty cycle. As you may notice, each period of the square waveform features a low level with duration t1 and a high level with duration t2. The duty cycle of the signal is defined as the ratio between the time t2 during which the signal is at the high level during a period divided by the duration of the period, so t1 plus t2. Typically, the duty cycle is indicated as a percentage, so this ratio is multiplied by 100, and to this product, the symbol of percentage is added. For example, in the case that T1 and T2 are equal to each other, then the duty cycle is 50%. So let us consider now a linear circuit and suppose that the input signal to that circuit, Vi of t, is a periodic signal. So a signal such that Vi of t plus the period capital T is equal to Vi of t. Now, a periodic signal can be represented by means of a Fourier series. In particular, if Vi of t is a periodic signal, then Vi of t can be written as A0 divided by 2 plus the sum for n going from 1 to infinity of a coefficient an, the cosine of n times omega 0 times t, plus a coefficient bn, the sine of n omega 0 times t. In this expression, omega 0 is equal to 2 pi divided by the period of the signal. A0 by 2 represents the average value of the signal. The coefficient an and bn can be computed as follows. An is equal to 2 over the period, the integral between minus the period by 2 and the period by 2, Vi of t, the cosine of n omega 0 t in the t, while Bn can be calculated as 2 over the period times the integral between minus t half and t half of vi of t, the sine of n omega 0 t in the t. Omega 0 is the fundamental angular frequency of the signal. This result tells us that a periodic signal can be written as the sum of an infinite number of sinusoidal contributions. Note that the frequency components are all integer multiples of the fundamental frequency omega 0. What is actually characteristic of each different periodic signal is the set of coefficients an and bn. The set of Fourier coefficients an and bn form what is called the discrete spectrum of the periodic signal. The superposition principle lets us compute the response of any linear circuit stimulated with a periodic signal simply by considering the response of the circuit to each of the sinusoidal contributions appearing in the Fourier series of the input signal.
By manipulating the Fourier series for the signal Vi, we can obtain some interesting result for the signals in the phasor domain. First of all, by considering the expressions of an and bn, one can easily find out that an is equal to a in minus n, and bn is equal to minus b in minus n.
Second, remember that the cosine of x is an even function of x, while the sine of x is an odd function of x. Based on these considerations, the periodic signal Vi of t can be rewritten as the sum from minus infinity to plus infinity of an by 2, the cosine of n omega 0 t, plus bn by 2, the sine of n omega 0 t. This same expression can be written again as the sum for n going from minus infinity to plus infinity of an by 2, the cosine of n omega 0 t, plus bn by 2, the cosine of n omega 0 t minus pi by 2. Let us consider now the nth term of the Fourier series in this new form. This term is given by an by 2, the cosine of n omega 0 t, plus bn by 2, the cosine of n omega 0 t minus pi divided by 2. This sum of sinusoidal signals corresponds to the sum of two phasors, one given by an by 2 times e to j times the phase of the first term of the signal. The phase is 0, so e to the j0 is 1, plus bn by 2 times again e to j, the phase of the second term of the signal, which is minus pi by 2. So e to minus j pi by 2. Of course, e to minus j pi by 2 is minus j, so this sum can be written as an divided by 2 minus j times bn by 2. Let's call an by 2 minus j bn by 2, which is a phasor, simply Cn. To be able to further manipulate the Fourier series for Vi of t, let's recall that the cosine of x can be written as e to the jx plus e to the minus jx divided by 2, while the sine of x can be written as e to the jx minus e to the minus jx divided by 2j. Now, by replacing the cosine and sine functions in the Fourier series for Vi of t with the expressions of the cosine and the sine we have just written, we get Vi of t is equal to a0 by 2 plus the sum for n going from 1 to plus infinity of an times e to the j and omega 0 t plus e to the minus j and omega 0 t divided by 2 plus bn times e to the j and omega 0 t minus e to the minus j and omega 0 t divided by 2j. If we collect e to the j and omega 0 t and e to the minus j and omega 0 t, this same expression can be rewritten as a0 by 2 plus the sum for n going from 1 to plus infinity of e to the j and omega 0 t times an by 2 minus j bn by 2 plus e to the minus j and omega 0 t multiplying an by 2 plus j bn by 2. Recall now from previous discussion that the coefficient bn is equal to minus b in minus n, and that an is equal to a in minus n. Therefore, the sum for n going from 1 to plus infinity of e to the minus j and omega 0 t multiplied by an by 2 plus j bn by 2 is equal to the sum for n going from minus 1 to minus infinity of e to the j and omega 0 t times an by 2 minus j bn by 2. Eventually, Vi of t can be written as the sum for n going from minus infinity to plus infinity of e to the j and omega 0 t times an by 2 minus j bn by 2. But an by 2 minus j bn by 2 is what we defined before as the phasor Cn. Therefore, Vi of t can be written as the sum for n going from minus infinity to plus infinity of Cn e to the j n omega 0 t. This final result tells us that the periodic signal Vi of t can be written as the sum of the phasors corresponding to the Fourier series components of the signal, each multiplied by e to the j times the relevant angular frequency and omega 0 times the time. One last manipulation to obtain the expression of Cn. We define Cn as an by 2 minus j bn by 2. We can now replace an and bn with the relevant integrals and obtain Cn as 2 over the period times 1/2 the integral between minus t half and t half of Vi of t, the cosine of n omega 0 t in the t, minus j 1/2 the integral between minus t half and t half Vi of t, the sine of n omega 0 t in the t. With some simplification, this is equal to 1 over t, the integral between minus t half and t half of Vi of t, the cosine of n omega 0 t minus j the sine of n omega 0 t in the t. Eventually, recalling Euler formula, which is e to the j x is equal to the cosine of x plus j the sine of x, we can write the expression of Cn as 1 over t, the integral between minus t by 2 and t by 2 of Vi of t e to the minus j and omega 0 t in the t. Let us consider now the circuit where a periodic signal Vi is applied to the series of a resistor with resistance R and a capacitor with capacitance C. Since, as we said, Vi of t is a periodic signal, it can be written as the sum for n going from minus infinity to plus infinity of Cn e to the j n omega 0 t, where Cn is the phasor associated with the nth frequency component of the periodic signal. The signal I of t, which here is considered as the output signal of the circuit, can be obtained by means of the superposition principle as the sum of the responses of the circuit to each of the frequency components of the input periodic signal. In particular, I of t will be a periodic signal with the same period as the input signal. The current I as a function of t can therefore be written in the form I of t equal to the sum for n going from minus infinity to plus infinity of Cn prime E j and omega 0 t. I of t includes the same frequency components as the input signal. This is what we expect from the application of the superposition principle. Cm prime is the phasor associated with the nth frequency component of I of t. The resistor and the capacitor in the circuit are in a series configuration. Therefore, the two components can be replaced with a single equivalent component with equivalent impedance ZEQ equal to the sum of the impedance of the resistor and the impedance of the capacitor. This is equal to R plus 1 over j omega c. Now, in Vi of t, the phasor associated with the frequency component omega equal to n omega 0 is Cn. In the case of the output signal I of t, the current phasor associated with the same frequency component n omega 0, Cn prime, will be equal to the voltage phasor Cn divided by the equivalent impedance, which is equal to Cn divided by R plus 1 over j omega c, and eventually to Cn divided by R plus 1 over j and omega 0 c. Note that in order to obtain this result, we have just applied the extension of the Ohm's law in the phasor domain. So the nth current phasor component is equal to the nth voltage phasor component divided by the equivalent impedance. Moreover, the result we got for Cn prime holds for n going from minus infinity to plus infinity. Therefore, I of t can be eventually be written as the sum for n going from minus infinity to plus infinity of Cn divided by R plus 1 over j n omega 0 c times e to the j n omega 0 t. The result we got in this specific case can actually be extended to any linear circuit. To conclude, we can say that the results we obtain for linear circuits in sinusoidal regime can be extended to the case of periodic non-sinusoidal regime.